Hello everyone, welcome to lecture 2 of week 9 of the course Power Network Analysis. This discussion is going to be the last discussion of module 7, which is Power Flow Analysis. In the previous lectures related to this module, we have extensively talked about or discussed about the essence or reason behind solving or understanding power flow analysis. Why do we need to solve power flow equations? And we have extensively talked about solving these equations for steady state analysis of the typical transmission network, which is meshed, has low R by X ratio, assumptions behind power flow analysis about the network, that the network is balanced, can be represented in a single line diagram on a per unit basis. All those with those assumptions, we have discussed about the techniques involved in solving power flow equations for transmission networks. Today's discussion, we will exclusively talk about a technique which serves the purpose of solving the same set of power flow equations but for low voltage or medium voltage distribution networks. The question is, why do we need to have a separate technique? One of those techniques which we will discuss is backward forward technique, although there could be several other techniques which can be used and they are present in the literature. And one of those techniques which is popular is this backward forward technique, which we will discuss in today's discussion. So the question that comes is, why do we need separate techniques? Why can't the same Newton-Raphson or Gauss-Seidel method or fast decoupled method or DC power flow model or power flow technique which we discussed in the previous lecture, why can't they be used for the distribution networks also? So typical conventional power flow methods which we have learned for transmission networks, they cannot be usually used for power flow analysis of distribution networks. The first reason for not being applicable is that distribution networks are usually unbalanced networks. The transmission networks tends to be a balanced network, whereas distribution networks are usually unbalanced. Why transmission networks remain balanced? Because of one of the reasons for them remaining balanced is the transposition of transmission lines, where R, L, and C values, they more or less appear in similar quantum across all the three phases. That is one of the reasons. The secondary reason is that through proper switching or operation or shifting of loads, the transmission network per phase load or source level, they more or less remains balanced. In distribution networks, however, the story becomes completely different in the sense that the loads themselves need not remain balanced across all the three phases. By balanced, I mean all three phases. For a typical three-phase network, all three phases have same quantum of load or source connected to them. That means if there is a distribution three-phase line, then each phase of the line carries the same quantum of power, same quantum of current. The magnitude can be the same. The phase angles may be different by 120 degrees apart, which we'll again see in details in the next module on fault analysis. So distribution networks, this sort of a assumption is usually not at all applicable, because the distribution network tends to serve the low voltage consumers, customers, wherein each section of the three-phase line need not have all the three phases present in them. Some of those sections may only have one phase or two-phase line, and hence the three-phase representation is essential. The single line diagram assumption which we had for single line diagram assumption which we had for power flow analysis, that doesn't hold true. That is the primary reason. Distribution network being unbalanced is because of the nature of the loads which are being served by the distribution network. Also, the R by X ratio of the associated overhead lines or underground cables in distribution network, that value tends to be higher. It's not that the different type of conductor, obviously the conductor types are different, but the conductor material used in distribution lines and transmission lines, it remains more or less same. The number of cross-section windings, the number of composite conductors may be different for different networks. So in distribution systems, the conductor type remains more or less same as the transmission network. So the question comes is, the conductor type remains the same, why is this R by X ratio different in transmission? It is low in transmission and high in distribution. The reason for this aspect is because distribution networks are typically low voltage or medium voltage networks where typical operating voltage does not exist, at least in the Indian domain. That does not exist beyond 11 kV, 33 kV and beyond they come into the transmission or sub-transmission domain. So compared to a low voltage operation, 11 kV is in fact a higher voltage distribution system. Typical distribution system, if we talk about in the residential perspective, 415 or 440 volt 3-phase or 230 volt or 220 volt single phase operating voltage. Under such low operating voltages, compared to high voltages where transmission networks typically operate at few hundreds of kVs, the corresponding electromagnetic induction phenomena, which is responsible for sort of flow of power from source to load end, at low voltages, the corresponding electromagnetic phenomena, which we have discussed briefly during the traveling waves discussion, this phenomena becomes weaker under low voltages, and that's the reason why corresponding line reactance or capacitance values also tend to go down. So it's not that the value of R is changing, the value of R more or less remains the same. Under low voltages, when this electromagnetic phenomena effect is lower because of the low operating voltage, the corresponding X value tends to go down in distribution network, and that's the reason why R by X ratio tends to be higher. The resistance value remains more or less same. It is not significantly different if we talk about a cross-section of a transmission conductor and a distribution conductor. It's the value of X which is getting significantly impacted or lowered down in distribution network due to low operating voltage, and that's the reason why R by X ratio tends to be higher. Now, when R by X ratio tends to be higher, what we can understand or analyze from the perspective of Y-bus, that when we evaluate Y-bus for a network whose lines are having high R by X ratio, the corresponding real part of Y-bus, which is the G matrix, it will be significantly dominant compared to the imaginary part of Y-bus. Unlike in transmission network where B was more and G was less, in distribution network, the value of G would be more and the value of B elements, they would be lesser. Now, when the resistive component of the network tends to be dominant compared to the reactive component of the dominant, so the corresponding Jacobian matrices which we tend to evaluate, where for transmission network the diagonal entries are mostly significantly dependent upon the values of B and not so much on the value of G, because the sine phase angle differences are more or less similar to the phase angle difference. The quantums remain the same. So therein the Jacobian matrix also starts to have some sort of a deformity or a ill conditioning nature. That is not just one of the reasons why Jacobian tends to become significantly ill conditioned. The first reason obviously is because Jacobian is dependent upon the Y-bus matrix. Jacobian also starts to become ill conditioned because of the nature of distribution network, which is that the distribution networks are mostly radial in structure. They have either one single in feed or one source system for conventional passive distribution networks. With multiple sources present in the network, we would still have one slack bus or one angle reference bus with several thousands of PQ buses and very rare or none PV buses present in case it is a passive distribution network. So this radiality of the network structure, it also affects the Jacobian matrix to some extent. In fact, that's one of the primary reason why it affects the Jacobian significantly. The Jacobian in distribution network for Newton-Raphson technique or for fast decoupled technique or for DC power flow technique, it tends to become ill conditioned. And once this becomes ill conditioned, its factorization cannot be done and hence solution cannot be obtained properly. For fast decoupled technique, the decoupling aspect is again, which we consider that P is mostly dependent upon phase angle, reactive power Q is mostly dependent upon the voltage magnitude. So the decoupling aspect is no more valid. R value has gone up, X value has gone down in terms of the transmission, in terms of the distribution network line parameters. So Jacobian value becomes highly in-condition or rank deficit. Typically in distribution network, the way the way distribution lines are modeled, unlike in transmission network where we had node J and node I, or maybe I'll use a different notation, not the node J, let's say node M and node M. If there's a bus which is having, if there's a line which is connected to buses M and N, then we had assumed the corresponding nominal pi model for the line where the half line susceptances were present, which are YSH, YSH, and then here we had the corresponding series line impedance. This was on a single phase equivalent representation. Since in distribution network, this line itself need not have all the three phases A, B and C. So it becomes furthermore important to represent each phase of the line present in the distribution network. That is point number one, and that's where you would find ZAA, ZBB, ZCC, the series line impedances. And the lines are also have mutually coupled. In fact, the mutual coupling effect, because of closer vicinity in distribution networks, the impact goes up. So ZAB, ZBC and ZAC, they represent the mutual impedances or mutually coupled impedances between the phases, and the corresponding admittances half line part, they are present on the either side. This is for the typical distribution line network model. Similarly, for load model, all the three phases, they have to be considered together in order to represent the corresponding load behavior. It may happen that one of these loads values may not be present at all. It might be that there is just a single phase or two phase load, or just a single phase load, which is typical residential load. So depending on the type of load which is present, all the three phases need to be present or considered together. The single phase equivalent representation of network, it will no more be valid. So what do we do? That is where one of the most popular techniques, backward forward technique, comes in. We will focus on a very simpler version of a typical distribution network or feeder, wherein the numbers which are sort of present inside these rectangular buses, they would represent the node numbers or bus numbers, whereas the numbers which are present within these simple brackets, they would refer to the line number or the branch number. So in this typical distribution network or feeder, there are 10 nodes present, 10 buses, because the last rectangular box has the number 10 present in it. And all these 10 buses, they are mostly radially structured. And so one would wonder, what do I mean by a non-radial structure or a mesh structure? The mesh structure would happen when I would have some circulating path present in this distribution network. So for example, if bus 2 and 7 are connected by a branch, bus 8 or 7 are connected by another branch, I would have two circulating paths. In case one path in this particular circulating branch is away, the distribution loads will still have alternative routes to get their power in feed from. In typical radial structure, if one branch or one path is disturbed or perturbed or is experiencing a fault, because of which this line becomes non-operational, the entire network loads, they will have no other path to get their source supply from. So that's the essence or reason or explanation behind radial network. So we have a simple 10 bus distribution network which are connected by 9 branches or 9 lines. And for explaining backward forward technique, I will keep the discussion limited. I'll make the assumption that the network is a single phase network. Although the discussion that we would have can still be applied for a three-phase network. So please have patience. We'll come to a three-phase network discussion in a moment. So what we do, the technique, as it says, backward and forward method. So there are certain steps in which the calculations are done in a backward fashion, and then the second part of the technique requires certain calculations which we would call them as forward calculations. So backward and forward terms, they come in from these calculations perspective. And to give you a brief essence, what do I specifically mean by backward calculation? It is all to do with the bus number where I am currently present while applying the backward forward technique. If I am present, or if my calculations are evolved around bus 10, and I do certain calculations which would shift these numbers or calculations closer to the source end, that is starting from the far end node, if I do certain numbers, if I do certain evaluations, and those numbers try to bring me closer to the source node, which is bus number 1 here, then that calculation or phase would be called as the backward phase. In the next phase, if I do certain evaluation, let's say I have reached source number 1 in backward mode, and now I want to go back to the last end node. So if I do certain calculations which would move my numbers or calculations away from source node to these far off nodes, then that phase is called as the forward mode. That's the basic essence. What are these backward and forward steps involved? So we choose our bus 1 to be the angle reference bus whose voltage magnitude is usually known. It would depend mostly on the transformer tap, which is depend on the trap position of the distribution transformer or substation transformer which is present, which is connecting this distribution network with the sub transmission or medium voltage distribution grid. So we are not considering the impact or presence of this. Whatever tap position has been set, according to that the voltage magnitude has been set here, and we are coincidentally choosing the same voltage magnitude as base voltage. So our voltage magnitude has a number of 1 pu over it. For angle reference, we are choosing for convenience 0 degree or 0 radian as a reference. Although this number could be different from 0 degrees or 0 radians. And the way we chose initial flat start for all other voltages, we choose a similar preferably flat start voltage. Based on this flat start voltage, we try to do our first step, which is the backward step. That is, based on this initial choice of voltages, in the backward phase, we start from the far end or tail end nodes and try to evaluate the corresponding line currents which are satisfying the KCL, or basically the KCL at this node. We apply KCL at every node where loads or source might be present, and based on this KCL, if there is a current which is being drawn from this node, then this current essentially has to come from the branch number 9 which is connecting 6 and 10. So based on the KCL application, we find these branch currents, and once we find the upper branch current, we try to apply KCL again at node number 6 to find the next branch current which is between 4 and 6, and that's how we can get the current from the source end, what is the current which is being drawn from the substation end. In the next phase, which is the forward phase, having obtained all these currents, we try to update the voltages at each of these nodes by applying KVL. So basically KCL is all about, backward phase is all about KCL application, whereas KVL is all about KVL application. Based on the latest currents in the branches, we update those voltages, and this sort of backward forward process continues till the voltages don't change significantly or the line currents don't change significantly. So what do? We start with, since the backward phase is the first phase, so we start with the farthest nodes possible. The farthest nodes from source end are node number 7, 8, 9, 10 and 3. So we focus on node number 9, that is, so we focus on node number 10, I guess the box is mistakenly present here. It's actually the box present over line number 9, which is connecting bus 6 to 10. The same, however, logic could be applied to this box also. So on bus number 10, we might have a load whose complex power is given SD. 10 represents the bus number. The bus may also have a source connected to it in case it is the active distribution network. So that generated power is also known as G. So essentially, the net power which is being drawn from the bus 10 is essentially SD10 minus SG10. If the demand is less, generation is more, the value of S would automatically be negative. If the demand is more and generation is less, the corresponding S would be positive, either in real or imaginary domain. And if this is the complex power which is being drawn from the bus, then this complex power essentially should come from this line itself. There is no other path for this line to have power from. So this S has to flow from this current line. In order to have that line carry this power, the corresponding current which it should carry is basically I10 naught conjugate. The conjugate here is the conjugate value I conjugate which we evaluated during power evaluation. So if this is the current at bus 10 and the only path for this current to flow is through the line, so we know what is the line current in the initial estimate. 0 here refers to the initial iteration, I would say, or recursion, call forward backward, you call it recursion. 0 would refer to the initial recursion. So we have now known what is the current in branch number 9 in the initial recursion. Similarly, we can apply the same KCL or power value evaluation for node number 9 and we can get the current in branch number 8. Once we know the currents in branch number 8 and 9, the only path for these currents available is through branch number 7. So we get branch number 7 current while considering the injection at bus 6 and power currents and the currents in line number branch number 8 and 9. And this sort of a current evaluation continues till we reach the current in branch number 1. Once we have arrived at the currents in branch number 1 and we intermediate also know the remaining branch currents, that completes one phase of backward step. In the forward step, using the same currents, so in the backward step, we moved from the far end to the source end. This is the backward phase in which the currents were evaluated by KCL application. In the forward phase, we would move from the source end to the far off ends by applying KVL and updating the voltages. So we start from the source end voltage cannot change because of the tap position or distribution transformer. So the voltage that can only update itself is the voltage of bus number 2. 1 here refers to the next update of voltages. So that basically 0.5 step is recursion is because of backward phase and 0.5 phase is because of the forward phase. And using these same currents, depending on the impedances present in these branches, we can find the corresponding voltages and do the same step till we reach the far end voltage nodes. This sort of a process would continue till the convergence happens. The convergence might happen in case when voltages don't change, currents don't change, or the power valuations don't change. This is all about for the case when we have single phase distribution network. And as I mentioned, when you have 3-phase distribution network, all the 3 phases have to be evaluated. So essentially, if I were to talk about one such backward phase equation, here I had only one single phase network, single phase demand and single phase generation, so one single equation was sufficient. When I have a 3-phase distribution network, I will have to evaluate these currents based on per phase basis, and then depending on these per phase currents, once I get my backward step, in the forward step, the impedances have to be 3x3 matrices instead of 1x1 matrix, because it's a 3-phase network. So 3 phases might have different impedances. These impedances might also be mutually coupled, and that is essentially what is shown over here in terms of these 3x3 Z matrix, and the corresponding backward phase which can be done for per phase basis is also shown over here. So essentially, in single phase network where we had one equation for one node and one branch, in 3-phase network we would have all the 3 equations coupled together because of mutually coupled impedances. And the same convergence process would continue till we get the solution for 3-phase network, although there are ways of how this process can be made much faster, and we are not going to discuss that because of simplicity. I'll conclude this discussion with a unique example wherein I have a 3-phase radial distribution network where, why am I calling it as distribution? Because each line is having an impedance Z where the value of R is much larger compared to the value of X. Bus 1 is to be considered as the substation bus whose voltage magnitude and phase angle are already specified in the example. And each of these remaining buses, that is bus 2 and bus 3, which are connected through impedances Z and Z in between, we have considered two cases. In one case, this load, which is P plus J 0.5 PQ, basically the real power demand is P, the reactive power demand at every such bus is 0.5 P. That is the understanding behind this complex power being given for every bus. And we choose two scenarios. In one scenario, the load is 0.43388,370 per unit, and in the second case, this 0 becomes 2 per unit. That's, I mean, two values. That's the only difference. And through this example, I'll try to explain that why Newton-Raphson technique has difficulty in getting voltages of bus 3 and bus 2 for this simple radial 3-bus distribution network. And on the other hand, how forward-backward technique can still give a desirable solution, the same solution in fact, with no convergence problem at all. Often in backward-forward technique, the term sweep also comes in, because the way backward-forward calculations are done in backward phase, you are sweeping from the tail end to the source end. In the forward end mode, you are sweeping from the source end to the tail end. So sweep term refers to that. So for our first load case, where P is 0.43388,370 per unit, we evaluate the Y-bus matrix, find the power flow equations. You can apply rectangular coordinate solution or polar coordinate solution. Either way, the application of Newton-Raphson technique would remain the same. And when we try to solve for Newton-Raphson technique, the solution that we get takes about 35 iterations with initial flat start as the voltage values. There are no PV buses involved, only 2 PQ buses and 1 slack bus. And after 35 iterations, this is the final solution obtained in per unit. Please note that these angles are all in radians and not in degrees, okay? These are in radians, not in degrees. This is the solution obtained for this 3-phase radial distribution network for Newton-Raphson technique. And you can imagine or wonder the number of iterations involved. There are 35 in number, which is substantially higher even for such a small 3-bus network. And this 35 iteration is based on the convergence check that was made on the mismatch vector equation used in Newton-Raphson technique. What is that mismatch vector technique? So we'll come back to this in slide number 12 preferably. For the backward sweep technique, for the backward phase, we choose the initial start of voltages, flat start working around with the currents I30, the injection current, find the corresponding branch current, which is I230, then find corresponding injection at bus 2, which is this current here, the one arrow shown over here, and eventually we arrive at I120 by applying KCL. Once we know I120, we use the same currents to update our voltages, and these voltages now have been updated. They are not at an angle 0 per unit, so the equations values remain the same as shown over here, and this completes one backward forward sweep method. In terms of convergence check, as I mentioned in slide number 10, we use the typical polar version of voltage coordinates and try to find the mismatch vector in Newton-Raphson technique the way it was done in Newton-Raphson analysis discussion. And the corresponding f of x, which I was referring to, it refers to the real power equation of bus 2, real power equation of bus 3, reactive power equation at bus 2, and the reactive power equation at bus 3. So this is P equation for bus 2 and 3. These are the Q equations for bus 2 and 3. I have avoided explaining how these equations have been obtained, but you can refer to the Newton-Raphson technique discussions where the polar version of equation forms for P and Q for PQ buses were discussed, and from there you would definitely be able to find these numbers or forms. So basically you have to find the Y bus for this 3-bus network based on the impedance values or admittance values given over here, and then when you plug on those corresponding admittance values, you would get this as the corresponding equation form. So if we evaluate the mismatch vector, because we are trying to compare Newton-Raphson technique with backward forward sweep technique, if we evaluate this mismatch vector at this latest solution, voltage solution, then the corresponding f of x that we would get is of this particular order. This is a 4 cross 1 vector, and after 20 recursions, the maximum absolute value, so infinity norm here is the maximum absolute value of this 4 cross 1 vector, which is a mismatch vector. This number turns to be somewhere around 10 to the power of the order of 10 to the power minus 3 or 4, whereas after 220 recursions, the number is significantly lower, of the order of 10 to the power minus 6, minus 7. And the final solution that we get, it is more or less same as the solution that we got for Newton-Raphson technique as shown in slide number 10. The numbers here, they are more or less similar. There are minor differences in the phase angles that we have obtained in terms of radians, but the voltage magnitudes and the, in fact, the phase angles to the fourth or the fifth decimal, they are more or less same. So the question now comes is that backward forward sweep technique, the observation is, not the question, the observation is there are no matrix factorization involved, and the effort required to solve either 20 recursions or 200 recursions is much smaller than the 35 Jacobians which were factorized in each of those 35 iterations of Newton-Raphson technique for this particular value of P. The situation becomes furthermore tricky when we just increase the load by a very insignificant quantum. For P is equal to 0.4338837 per unit instead of the previous value of P. The initial Newton-Raphson solution remains the same, but if we try to look for convergence of the Newton-Raphson technique with a similar convergence check that we have been using, Newton-Raphson technique never converges nor diverges. It keeps on iterating, and the number of iterations, even if they are tending to infinity, the numbers will never ever match. Whereas for the same load, the backward forward sweep technique takes the same number of recursions, 20 recursions if we talk about minus 3, minus 4 PU convergence, or 10 to the power minus 6 convergence for forward backward sweep technique, the same exact solution with minor differences because the load has now changed. The same solution is obtained in backward forward technique with not much of a difficulty at all. In the next lecture, we will start with our new module, which is fault analysis, and try to understand why fault is the problem in power networks, how our synchronous generators behave during this fault period, and that is where the parameter variation of synchronous generators and corresponding time constants would come into picture. Thank you.